everybody. So pleasure to be here, and also would like to thank again the organizers, not only for the conference, but also for this fantastic dinner last night at this fantastic place. So thank you. So it's obviously an honor to speak then as the first speaker the next morning after the dinner. And I should talk about the prospects in Neutrinos double beta decay. And there have been plenty of very interesting talks giving already perspectives for the different projects. So what I will try is, on one hand, to wrap up a little bit, repeat some of the developments, and also cover some of the projects which have not been discussed so far during this conference. So just as a starter, it's clear what we are looking for is the neutrinoless double beta decay, which is first of all a lepton number violating process. There's a little bit of an echo, or maybe, yeah. So it's clear that this is physics beyond the standard model, and it's clear that also this would imply that neutrinos do have a Majorana character. This doesn't mean that this is obviously the driving mechanism, but at least at some academic level, they should be of Majorana type. The signature we're looking for is a peak at the Q beta beta value, and there are two electrons coming from this vertex, and this signature can be used for identifying the topology. You know, we don't only want to measure the energy, we also want to know that this is not a background event, but this is really a true neutrinoless double beta decay. So in our standard paradigm, we always connect the neutrinoless double beta decay with the neutrino mass, the mass mechanism, and then you have obviously a clear relation between your half-life, which you measure, and the neutrino-related parameter, the so-called effective neutrino mass, which is the famous coherent sum over the mass eigenstates here, and coherent because obviously the mixing parameter can be complex, and you can have also some cancellation. The nuclear physics enters through the nuclear matrix element, and obviously through this phase space integral, which can be calculated precisely. So also well known is the fact that we have predictions about the effective mass coming from oscillation experiments, and here the famous Visani plot for our different realization, whether neutrinos are degenerate, so basically sitting at the electron volt scale somewhere, all masses, or we have an inverted ordering where we have a lower bound at between 10 and 20 milli-electron volts, or you can have basically the normal ordering, where depending on your parameter combinations, you also can have some cancellation for some parameter range, and the numbers which you could then produce, or the half-lives, are incredibly small. So for the time being, I mean, we don't have a clear picture whether we have a normal ordering or inverted ordering. There might be some slight hints in direction of normal ordering, but I think there needs more experiments to become and to clarify this question. Nonetheless, if you look at this plot, which is often shown, you always think, oh, that's quite depressing, because if it is normal ordering, then we never have a chance to observe that. But this is obviously not completely true, because, I mean, this is a double logarithmic plot, and now different groups have done some analysis, throwing dices and saying, well, as long as we don't know basically what the true realization is, and you can basically then find different realization in nature. So what Agostini, Benato, and Jason Detweiler, who is also here present today, done in their analysis, they made a global basin analysis, basically taking all the oscillation information available, measurements on the direct mass measurements, cosmology, and then basically define priors in a basin scheme, and saying, well, we don't know anything about the Majorana phases, we just take them as a flat, and we throw dices according to such a distribution. And then basically the other question was, well, how to treat M1, and you can treat it either on a linear scale or you can scale invariant, and still you have to decide on which base you throwing your dices. They decided to take as a basis the cosmology, the total mass, and then they find basically a probability distribution for the normalization for the inverted and the normal hierarchy. And you see here, it's rather unlikely that you find a combination which basically leads to full cancellation. And you see also here the color code, you have more realization here at the higher part. So basically you can then look for the probability distributions, and here they showed, for example, the cumulative distribution. Let's take here the inverted ordering. So if you have an inverted ordering, you have an experiment which comes down to 10 to minus 2 millielectron, 10 millielectron volt, then you have basically, you can cover completely this parameter range. But I think more important is that what they saw is under the assumption of these priors, you have a good chance, more than 50%, 60%, that even for the normal hierarchy, you see a signal. So that's, I think, an important part. Obviously, if there's now a physics reason which drives M1 to very low values, so set it, for example, to 0, then it's clear, obviously, then it moves down here, and the effective mass goes here to the millielectron volt range. So the takeaway message is, so as long as we don't have a theory which tells us basically where M1 and how the phases should be, and if everything is equally likely, then you have also with the next generation a very good chance, 60% chance to see a signal here for the normal ordering, not only for the inverse ordering. Now if you go beyond our three standard neutrino paradigm, Carlo Giunti has discussed that in his talk the other day. Well, you have 1 degree of freedom more, given if you're at the electron volt scale sterile neutrino, and with the hints of mixing you have, the picture turns around. Suddenly the normal ordering has some lower bounds. Obviously you can have also cancellation, and for the inverted ordering, basically here the picture looks like that. Here you can have obviously here a cancellation and get very small values. So, but you can also go say, let's forget about our 3 neutrino paradigm, and this is not what is driving the neutrinoless double beta decay, but something else. And here this is taken from Werner Rodejan's presentation at Taub. You can come up with many theories beyond the standard model. They all predict lepton number violation, and then this can be the graph is driving it, and you can basically derive by your observation either a limit or you can establish a decay. And here's shown the complementarity with LHC physics, looking for the same charged leptons. Basically, that's nothing else than the neutrinoless double beta decay graph turned around. And that's the reason why, for example, you can make this analysis where you compare basically what neutrinoless double beta decay experiments are producing and compared with LHC physics. So let me now, for coming more to the experimental side, obviously when we want to do an experiment, we question ourselves, do we use the right isotope? Is there from nuclear physics really one isotope which is superior to the other ones? And basically the compilation and also the discussion by Javier Menendez earlier this week, we have a spread about a factor of 2, and if you translate that here now in half-life, always in the 3 neutrino paradigm, you see here, these are here putting in numbers what you expect in 1 kilo, so 1 ton year exposure for the different isotopes. And you see basically it's a factor of 1, 3, 2, so we are talking about a factor 2 to 3 difference of decay for the different isotopes. So basically the choice which isotopes to use is really experimentally driven, how you can basically do the experiment where you can see so few events for a discovery. I mean, this has been at the beginning of the week long discussion. These numbers here are obviously taken here for an unquenched GA, and we assume that this is quenched. I think from the experimentalist side, we really would like that this is settled soon, that we really can plan, because obviously these numbers scale here with the 4th power of GA, and obviously these numbers can be much, much lower if GA was strongly quenched. So let me point out then, so if we have so few events, then obviously, and you want to go for a discovery, you have to have a very good signal over background relation. And here, this is a plot produced by Jason. where you basically show here, this is the discovery significance, so that's 50% chance discovery for a 3 sigma discovery. And here, this is the exposure. Now let's take, for example, make an experiment with 10 ton years. If you have 1 event per ton year, we're talking about 10 events roughly. Now, if you're completely background free, this would be obviously the ideal case, but you can only asymptotically get closer in this direction. An experiment which aims to having something like 0.1 counts per region of ton and year. So that basically means after 10 ton years, you have about 1 count as a mean value of background. And you see that's basically what you can reach. Then let's here as an example, 10 to the 28 years. Now, if you had a factor of 10 or 100 higher background, then you see immediately, let's take here a factor of 100 higher background, how long do I have to measure to get the same limit? And you see here, you follow that curve, you see where I come back to here, and you see that's nearly 2 orders of magnitude longer measurement time or larger exposure. So it's clear that background and exposure are strictly correlated, and you should really fight hard to get your background so low such that you have the best possible signal of a background ratio, and ideally you can get down to a signal background free experiment. So now this is a list of experiments which has been discussed this week, most of them, and let me just jump in a few of them and point out which I think are kind of the key developments for the future. And let me just start directly with Xenon and Nexo. Giorgio has discussed the future plans of Xenon. Nexo, which is a 5-ton enriched xenon observatory, which basically has it based on the successful EXO concept. Basically, you read charge and light, and then you basically can discriminate between single-site events. You have topology information, as in EXO, and you have basically energy resolution. And now here in their plot, they showed basically how the signal peaks out stronger and stronger the further you go into the inner part. And now, sometimes if we want to be nasty with each other, some people then say, well, the xenon is used for shielding outside and not for measuring, but that's obviously not the full story. That's not true, because, I mean, you have seen the analysis of Borexino, for example, where you have a multivariate analysis. You take the full information of the PDFs, so your radial distribution, your energy distribution, and then basically you take that information from the full detector, and it's not only you make a fiducial volume cut and look in the inner part. So based on their analysis, George has also showed already that plot earlier, how now here the discovery sensitivity and the limit setting scales with the exposure, and with a lifetime of 10 years. Basically, the discovery sensitivity is something like 6 times 10 to the 27 years, and the limit setting here is about close to 10 to the 28 years. The barium tagging, which is always being done R&D in various, so at EXO, Nexo, but also outside EXO, is obviously would bring a breakthrough in terms of completely being background free from, at least from radioactive isotopes, not from the 2 neutrino. There you have to have energy resolution. But so this would basically, if this can be implemented successfully, then this would push further the discovery sensitivity here above the 10 to the 28 years. So the other big xenon project is CAMLASN, and CAMLASN is currently, CAMLASN operates the loaded liquid scintillator inside a large liquid scintillator volume. In the moment, well, the last one was about 380 kilogram of enriched xenon. And they're currently, well, and they're derived here a strong limit. Here, the limit of combining all their data is something like 1 times 10 to the 26, to be compared with a sensitivity of 5.6 times 10 to the 25 years. You can see basically there's a kind of a gap of here. They have an underfluctuation that's basically given using a frequentist method. You get basically a much stronger limit than the sensitivity. Important, they are currently upgrading the detector, and end of this year, they want to take data again now with an increased target mass of 750 kilograms, and they have also long-term perspectives, which basically they say, okay, we have to improve energy resolution, and to energy resolution you have to have basically more light, read out higher density of PMTs, and that's what they called CAMLASN 2 Zen, and that's on their roadmap for the future upgrade. Now, another Xenon project is next, using a TPC, high-pressure TPC, and the interest of the high-pressure TPC is obviously that the energy resolution is superior to the liquid TPC just by fundamental physics principles. And the next collaboration has shown basically that you can have an energy resolution here of 0.7% at Q beta beta. So that's very interesting, and they basically really want to make use of the full topology, so 2 blobs at the end of these high-pressure TPCs. Barium tagging is also there, an important development, and I would just like to highlight an idea which has been, I think, brought up by David Nygren. Basically, there are fluorescence molecules, and if you succeed to take a barium atom, the daughter of the xenon, chelate it with this fluorescent molecule, then you can basically do a single atom counting by fluorescence. That's in biophysics or biology, basically is being used already, so you can count very often the same atom and look at the fluorescence, and if it's and so you can do a single photon counting. How to combine that now, this method with a TPC, get the barium out, mount it here, do the laser spectroscopy, obviously that's the challenge, that has to be shown that this can be done. But I mean, there's a potential of a real breakthrough in barium counting, I think, from my point of view. Now, let me now come to the cryogenic detectors, and there have been several talks yesterday by Maura Pavan, Oliviero, and Cremonesi, and so you saw you saw already plenty of them. Let me just go very quickly through it again. I mean, you know, it's a major development done by the, led by the Milano group, coming from Coricino to Cuore, which is basically running now. The concept is you go to very low temperatures, the heat capacity basically gets smaller and smaller, and then basically measuring energy here basically drives your signal, and you can get excellent energy resolutions. So Oliviero showed here this plot early this week, which shows the signal region and the background, and they provided a new half-life at the Taub conference already, and next week they will update the latest data set. And important is basically they do not see a signal, and they can derive a limit so far, and that's about here 5 times 10 to the 24, and if you combine it with earlier Coricino data, then it's about 6 times 10 to the 24 years. So important is here the background is dominated by surface alphas coming from basically the surrounding material on the crystal and on the holder. Despite a tremendous effort, they have succeeded to improve that over Coricino, but still that's the background which is limiting them. And for that reason, they're doing heavy R&D in the frame of Cupid, that you use also the light information. And there are 3 lines of R&D. One is the zinc selenide, the Cupid selenium, Cupid 0. There's molybdate, so lithium molybdate crystals, and then there's the Cherenkov way to discriminate. Here, I mean, there's in this way, the concept is alphas do not produce Cherenkov lights, while electron and gammas are doing Cherenkov light, and you can basically discriminate them effectively. Obviously, all your light detectors you have to bring in should not bring in background producing gammas, because that's obviously you cannot discriminate. So, but it's a very efficient way to get rid of the alphas. Similar here for the lithium molybdate, the scintillating crystals, where you basically have use again here the different light yield and heat channels for the alphas and for the betas. So there's also a project in Korea, which is called Amore project. Also, they base on molybdate crystals, and they are also running already first test runs, and they want to scale up here up to 2020 about 200 kilograms of molybdate crystals and operate that then at the new underground facility in Korea. So let me now come to the last part, the germanium detectors I would like to discuss today, and that's about Gerda, Majorana, and the Future Legend project. So Jason Detweiler presented the first Majorana demonstrator results here yesterday, and so they have the best energy resolution, so 2.5 kV at full width half maximum at Q beta beta, and they operate these germanium detectors in a high purity copper shield inside at the SURF underground facility. And also in germanium detectors, you have some background from surface alphas, which are sitting on the P plus or the open surface. And these germanium detectors, now the Majorana detectors, they use a particular pulse shape feature, which they call the delayed charge recovery, that you can basically identify these signals, alpha signals, from good signals. And you see here, this is a calibration spectrum. Here are the good signals, and these are the alpha signals. And then you basically can make a very efficient cut and get rid of that. And they have shown now and released here at this conference for the first time that the background they can achieve is about 4 counts per full width half maximum ton years, or if you translate it into per kV ton years, it's about 1.6 counts per kV and ton year. So you see here the red dots are those which stay over, and these are just basically 3 events. Here 3 events in a 400 kV window with this fantastic energy resolution. So basically it's, in that sense, also a background-free experiment, counting background-free within the exposure, the design exposure. So Gerda at Gansasso is very similar to that of Majorana. The concept, however, is that we operate germanium detectors in liquid argon as bare detectors, and we do instrument this liquid argon with light readout structure. And inside we have here a germanium detector array. So it looks like here, and individual detector you see here is a low mass holder, and here directly bonded to the detector. We try to avoid as much as use as little as mass, and then basically operate the liquid argon as an anti-coincidence system, and not only as a coolant and a high purity shield. And this is then has been built and is operating. Here's some pictures of it, and let me show you here our liquid argon readout, which is built here on a wavelength shifting fiber system. So you want to get close to your detectors to pick up the light, but you want to have material which is super clean to get close to it. So you cannot put a photomultiplier close by. That's much too radioactive. We have some PMTs at the top and the bottom, but these are high purity fibers read out with silicon PMs just in dye to make sure that the radioactivity is not hampering our background. How that works is shown here in this plot. So this is a calibration spectrum with a thorium line, and you see here basically if you do just a liquid argon veto, you come here from the dark gray to the light gray. If we use pulse shape discrimination, similar as what Majorana is doing for the Compton spectrum, you have a factor of 2 roughly, because only half of them are multi-site events. If you combine both of them, then you end up with this red. You see here the tremendous suppression power for this calibration source. It depends obviously the suppression on which calibration source you have, or which contamination you have, and it's clear that this is not a unique number which is equal for all contaminations. The spectrum which has been acquired in the meantime looks like that, and now this is before any cuts is the light one. Then we do the after the liquid argon cut, and you see here on the logarithmic scale here all the Compton from the potassium disappears, and here in this region also a lot of counts disappear. However, here this part, which are alphas, do not disappear because they do not create a signal in the liquid argon. So we have 2 sets of detectors, so-called enriched quarks detectors and the enriched Beji detectors. and let's focus really on these lower ones, because these are the phase 2 detectors, and what we want this kind of detectors also use similar to them in the future. So the question is, how do we get rid of these alphas? And very similar to what I've shown for the Majorana case, we also use pulse shape information, and we see basically that all the surface alphas are really well separated from our signal region. So the closest dot here is something like 5 sigma away. So basically we really identify them one by one and can discriminate them. And having a fantastic high acceptance of 87% for the zero neutrino candidate events. So that's the spectrum, how it looks after the analysis. And let's zoom into here for a moment. So that's basically the result which has been presented by Luciano Pandola at the TAUP conference. So here we are basically, with our new detectors here in 18 kilogram years, we have basically 4 counts, and that's the energy resolution where we're looking for, and from that we derived basically limits and said, okay, in the exposure of 100 kilogram years, which is the design, we'll operate background free. That basically means less than 1 count in the signal region. Okay, just as a last, I want to discuss a little bit about the future. Now Gerda and Majorana plus new groups have basically teamed up to build the so-called the legend collaboration, and making use of basically what we have developed both in Gerda and in Majorana, and basically combine best of them. And this is the new collaboration here. So it's, as said, not only the Gerda and Majorana, there are also new groups involved there. And the plan is the following. We start the first phase, which is legend 200, and there up to 200 kilograms of detectors will operate, and we want to reduce our background by a factor of 5 compared to what we have in the moment. We think we know how to do that. We want to reuse the existing infrastructure and then go for a design exposure of 1 ton year and reach a sensitivity of 10 to the 27 years. And then in the second phase, upgrade in a new facility up to 1,000, so 1 ton, and we have to reduce the background by another factor of 6 roughly to get to our design sensitivity, which is then for an exposure for 10 ton or 12 ton years to reach the 10 to the 28 years for discovery sensitivity. And here, this is shown here once again, discovery sensitivities here for Gerda Majorana at the 10 to the 26, then legend 200 at 10 to the 27, and 1 ton basically at the 10 to the 28 years. So we always go 1 step in exposure to cover this region. So I think I'm over with my time. I just flashed to my conclusion line, and would say, I think what we can say, I mean, there's strong activities worldwide to make the next step. I think we're more funding limited than experimental limited. We all want to search for lepton flavor violating decays. As said, the discovery potential for the inverse ordering is very high. It's reasonably high also for the normal ordering. And very important, I mean, 1 experiment is not enough, that's clear. As much as we should compete with each other, we need at least several, I think 3 or maybe 4 experiments to really to explore this range, to come down and have redundancy and look with different isotopes, different techniques to this signal. Okay, I think I stop here with the last said. I think the design which is changing from in the past to the future is really that we really want to make discovery experiments. So such that with a few counts we should be able to see a signal and say that's not a background. We not only want to set limits, we want to see basically a signal and devise the experiments in this direction. Thank you very much.
Thank you so much.